Okay, hi everyone. I am Sally Shaw from UC Santa Barbara, and I'm going to tell you about the LZ dark matter experiment. Okay, first of all, just a brief overview of direct detection using dual phase liquid xenon TPCs. Of course, I'm sure you all know the primary signal is a nuclear recoil of a xenon atom, and most of the backgrounds are, of course, electron recoils. We get the two signals, the S1 in the liquid and our ionization signal S2 in the gas. We collect the ionization using a drift field, and we're able to do pretty good electron recoil, nuclear recoil discrimination, thanks to using the ratio of S1 and S2 signals. So there's some examples from, actually, this is the LUX experiment, some calibration data showing how those recoils lie in different bands in the S1 versus log S2 space. And of course, we also get 3D position reconstruction in these TPCs. So you get your X and Y using your photomultiplier tube arrays at the top and bottom of the detector. And you get Z from the time difference between S1 and S2. So LZ is a relatively large collaboration of about 250 scientists, engineers, and technicians from about 38 institutions. So we have mainly universities in the US and national labs, but also in the UK, Portugal, and South Korea. This is an older collaboration meeting photo from up at the lab we are located in, which is, of course, the Sanford Underground Research Facility. And this is located in Leeds, South Dakota, which is actually where I am right now. It's a beautiful day here. And this is a sort of dedicated underground science facility in what used to be the Home State Gold Mine. But we're down at the 4850 level, which reduces your cosmic ray background by I think 10 to the 6. There are a whole host of low background experiments located at the Sanford Underground Research Facility, or SURF. And of course, this will be the home for the June FAR detector. I think this is an old diagram. It says LBNE. Of course, that's now known as June. Okay, so the LZ detector itself, obviously, it's like I already mentioned, it is a liquid xenon TPC. That sits in the very middle of this diagram here. It is 10 tons total of liquid xenon, but we have 7 tons active. We plan to use a 5.6 ton fiducial volume. So this is the biggest xenon target mass of its kind. We also have a 2 ton skin veto. So we have a layer of a liquid xenon that sits outside of the TPC that acts as a veto. We call it the skin. We also have 17 tons of gadolinium-loaded liquid scintillator, which is our neutron veto. You can see here that I've sort of put some key numbers on this slide. We have a total of 494 photomultiplier tubes inside the TPC, looking for light from the liquid and gas. And then we have 131 skin PMTs that are instrumenting the outside and the bottom of the detector, of the sort of skin region. And then 120 of the sort of larger 8-inch PMTs sitting outside within the water tank, which I'll talk more about how that system works later. And yeah, this whole thing is sitting inside a 60,000 gallon water tank deep underground. So you can see here some other things I pointed out, like, for example, calibration tubes. Okay, let's talk a little about the xenon itself. Like I said already, we have 10 tons total. The xenon undergoes a series of things to make sure it's very, very pure and clean to keep backgrounds down. So one of these is krypton removal. So this happened at SLAC. There is going to be a dedicated talk to that. So I will by Drew Ames on Friday. So just a little advert for his talk there. But the system uses gas charcoal chromatography to remove krypton from xenon, and our goal is less than 300 parts per quadrillion of natural krypton over xenon. So we also do online purification of the gas xenon using a hot zirconium getter to remove electronegative impurities. And the full 10 tons is purified every 2.4 days. There's also an inline radon removal system, since radon is one of the worst backgrounds for these kind of experiments. And this uses an activated carbon trap that reduces radon by 10 times in one pass. So the TPC itself, I already said we had 494 PMTs. These are Hamamatsu R11411020 PMTs in the top and bottom array. I believe this is the bottom array. You can see here in this really beautiful photo of that array when construction was completed. We also have 4 electrodes or grids that were woven on specialized looms. This happened at SLAC too, and they were passivated. I think Jinke just mentioned this to reduce the electron emission. 57 field rings. That's a lot of field rings, but we have that many. They are embedded in PTFE. That provides a 310 volt per centimeter drift field. And our TPC was completed in August 2019. You can see a very beautiful photogenic photo of it after it had been completed. You can see that nice reflective PTFE that helps us collect light. Of course, we have PTFE not just on the inside of the field rings, but the outside too. And that's because of that skin layer that also we want to improve light collection for. And this was inserted into our inner cryostat vessel at the Surface Assembly Lab at SURF back in 2019. And there will be a talk by Ryan Linhan on those high voltage grids on Thursday too. So look, I already mentioned the skin a little bit, but a little more on that. There are, like I said before, there are 2 tons of active xenon between the inner cryostat vessel and the TPC, which is why you see the PTFE on the outside here. And then this bottom left picture is the inside of the inner cryostat vessel after it had been covered in PTFE. This is optically isolated from the TPC. We have 93 little PMTs that are sitting, we call them the ice cube trays that go around the top and look down at the skin. But there are also a number of PMTs down in the bottom of the detector, sort of in the dome region beneath the bottom array of the TPC. And the whole point of this skin, Vito, is to really tag gamma rays as they come in and out of the TPC, and we're expecting it to be more than 95% efficient. Okay, so I talked a little about vessels, cryostat vessels, but this was, another major piece of construction for LZ. We did, you see on the left there, that's the inner vessel that was installed. It was placed inside the outer vessel, inside the water tank back at the end of 2019. You can see a photo of the underground crew after the successful insertion of the ICV. And this titanium, this was one of the sort of our early achievements was locating a really low background source of titanium through lots of a huge radioassay campaign and lots of work with different vendors to try and find the right production methods, the right source for our titanium. And it is the most, the world's most ultra pure titanium. Okay. So I'm going to talk now a little about the outer detector. This is something that is quite unique to LZ, the way it's designed and the scintillator we use, but it's, I like to show this little diagram just to show you how it works. So if you have a neutron emitted into your TPC, neutrons are, of course, one of the most dangerous backgrounds for these dark matter searches, since they create nuclear recoils that look just like, could just look like WIMPs, especially if they only interact once. So if we have a neutron emitted, say from an alpha N reaction in something like the PMTs, you have a nuclear recoil inside the detector. The neutron will then exit, and then we'll actually enter our outer detector, and it will thermalize and then eventually capture on gadolinium or hydrogen. It's mostly gadolinium. Gadolinium has one of the highest thermal neutron capture cross sections, so that that's the whole point of having gadolinium in there. And when that captures, you get gamma rays emitted from the post-capture nucleus. For gadolinium, it's between 4 and 5. For hydrogen, of course, it's just 1 gamma. And these gammas, of course, then create scintillation light inside the scintillator, producing photons, which are detected by the PMTs. And the reason these PMTs sit a little further away from the outer detector itself is just because they are radioactive. So we allow for a water gap in between those PMTs and the outer detector system. So I don't think I actually said yet, but I should say that the liquid scintillator is contained within a series of acrylic tanks. So I could have some photos here. So we have 10 of these acrylic tanks. This is the area of LZ that I work on the most. So that's why I feature in this picture on the left here to try and show you I'm about 5'2". So you can see how big the these acrylic vessels are that contain our liquid scintillator. So we have 10 of them total. There are 4 side, I don't know why it says 3 there, it should say 4 side vessels, and 2 top and 3 bottom. And that's to provide a full coverage around the cryostat to try and snag any neutrons that are leaving our TPC. And then, like I say, we use 17 tons of GD loaded liquid scintillator. You see some barrels at the top there containing that. That was made at Brookhaven National Lab. And then this is actually in the Dakota warehouse in Rapid City, South Dakota, waiting to be transported to SURF. On the top right, we have to have a filling system to put our scintillator into our acrylic tanks, which is a whole complicated process by itself. So you can see a little picture of some of that filling system on the right there. It's a whole series of tubes and other acrylic vessels and pumps and all sorts. Bottom right is those PMTs, and as you can see, they are actually installed. So here's some photos from the installation of our detector. You can see the one of the side vessels being lowered into the water tank underground. These had to go in a long time ago. This was 2018, just because they're so big and we needed to get them in before we put the cryostat in. And they actually, you may guess from my color scheme that I do like pink, and I was allowed to choose the shipping frame color, so made for some cool photos. Some photos of the acrylic tanks. The top one there is when we were cleaning them. You can see that at that point the water tank was not a proper clean room, since we're just dressed normally. Then on the bottom there is when the acrylic tanks had all been moved into place. You can see that in the middle there, the outer cryostat is wrapped with Tyvek reflector to enhance light collection inside the outer detector. Top right is PMT and Tyvek installation. Bottom on the right there is me starting to install the fill system, so running tubes to attach to the acrylic tanks so that we could put scintillator in them. And that, of course, things were a lot cleaner by then in there, so we're all Tyvek'd up. But this construction was completed in spring of this year. Okay, so cleanliness and background mitigation is something to mention. I already just talked about, being clean inside the water tank. This has been a really intense effort for LZ to keep our backgrounds low so that we stand the best chance of identifying a dark matter signal. So we had, for detector materials, we've had radioassay campaigns, all sorts of gamma screening, ICP-MS, which is inductively coupled plasma mass spectrometry, and neutron activation analysis. So we've utilized facilities all across the US and in the UK too for different screening facilities. We've done radon emanation. We have 4 different screening sites for radon emanation, and we have assay panels that are portable that can be moved around underground. And then, our target radon activity is 2 microbecquerels per kilogram of xenon. Everything is, of course, constructed in radon reduced clean rooms. We try and keep dust to a minimum and try and reduce radon daughter plate out on our TPC walls. Xenon contaminants, I already talked a little about that, how we keep the xenon, we try and purify the xenon to keep those backgrounds down. And of course, our cosmogenics and externals are mitigated by going underground and then having the vetoes and the water shield. So backgrounds themselves, just to give you a quick summary of the things we worry about. Of course, there are plenty of electron recall backgrounds that are mainly gamma rays and beta decays from uranium and thorium chains. Also cobalt 60 is common, potassium 40. There are, of course, line decays within the xenon itself that we measure, and radon and krypton dissolved in liquid xenon. Now, nuclear recall backgrounds, which are, of course, slightly more dangerous. There are neutrons from alpha N and spontaneous fission in detector components. There are boron 8 solar neutrinos. And there's a final sort of nuclear recall background, which are not really actually nuclear recalls, but they are misreconstructed ion recalls from the wall of the detector. And the things we use to mitigate this, other than, of course, all the cleanliness and radioassay, but are also using, single scatter cuts. We only expect dark matter to interact once. Energy cuts, we're looking in a sort of narrow energy range at sort of tens of keV. We have fiducialization, which is only looking in the center of the detector, utilizing xenon self-shielding, and then our dual veto system at the skin and the OD. So on the right here, there's a demonstration of how applying that outer detector really significantly reduces the nuclear recoil background from the detected materials and actually makes the dominant nuclear recoil background neutrinos, which are of course pretty much irreducible. So that's what you want from a veto. So here are our sensitivity projections. So, we have, we're expecting 1.4 times 10 to the minus 48 centimeters squared at for a 40 GeV WIMP for spin independent scattering. There's some sensitivity curves on the right for your spin dependent scattering too, WIMP proton, WIMP neutron. And you can see that we're moving down. This is a sort of older plot. I know there's been better limits since set since this point, but this is from our sensitivity paper, so it's a little outdated. But we are moving down significantly in the space and really digging into this this shaded gray region, which is where theorists have looked at minimal supersymmetric models and decided that there really could be some dark matter there. So we'll also be getting really, really close to that neutrino floor where we start to just we start to see the neutrinos from not just the sun, but also the atmosphere and supernovae. And then we're going to start to face problems for dark matter detection. But of course, there are some ways around that people are looking into. But LZ isn't just about dark matter. We do have some significant sensitivity in other areas. So some of the sort of different physics that we'll be looking for with LZ are things like solar axions and axion, like ALPS axion-like particles. In particular, we have competitive sensitivity to neutrinoless double beta decay of xenon 134. You did just hear about the Migdal effect, so we are hoping to have enhanced sensitivity to low mass dark matter through that. And there's some other things here, leptophilic dark matter, mirror dark matter, neutrino magnetic moment. And there's some very recent publications on all these various sensitivities we expect to have that you can look at. So commissioning, we for our xenon systems, we did a circulation test that was completed last year, which we achieved the design gas circulation rate of 500 SLPM, and our TPC has been cooled down to 185 Kelvin. For our PMTs, they have all been now fully tested and characterized with LED calibrations in all three detectors. So I'm not sure if we can get this to play, but we have, for example, a visualization here of it's quite nice showing you this is real data of an optical calibration system injection, which is just LEDs in the outer detector system. On the right here, I've also shown some waveforms from the TPC and the OD, just showing that these things are working and the PMTs have all been fully characterized now. Okay, so that's it. LZ construction is complete. We have cold xenon. All our PMTs have been tested with LEDs. Physics data taking is this year. We expect a 40 times improvement in sensitivity on the current limits, and we're also sensitive to non-WIMP physics. So next year is going to be really, really exciting. Okay, thank you.
Thank you, Sally. It's a beautiful detector. It took years of effort to build. And I'm glad to hear that data will come soon and the fun will begin. That's also part of this conference. We build all this kind of detectors and solve all the technical issues. Let's see if there's any questions. Please raise your hand. Giovanni.
Hi, very nice, thank you. I'm wondering about the skin. Why you decide to have a skin instead of having all the cryostat fill with increase as much as you can the TPC for having more shielding, active shielding for the xenon, and minimize the materials like PMTs and Teflon as well.
Sorry, so was the question, why did we have a skin and not just a bigger TPC?
Yeah, I mean, I don't get where do you what do you gain? How do you gain in tagging efficiency for gamma rays from materials?
Yeah.
Since you also add a lot of materials, right?
Mm-hmm. Get back to the so basically just having that extra layer and it being instrumented, like I say, we tag gamma rays that scatter in an as they leave it or enter the TPC, and it just gives us that extra vetoing power. Like it's I don't have a better explanation than that. We've seen that having 3 detectors that can tag, one in particular focusing on neutrons and one focusing on gammas, is really, really useful for fully understanding our radioactive backgrounds. So, and most, gamma rays do interact. There's liquid in the skin, so that there's plenty of material for them as they exit the TPC. So, yeah.
Okay, so you gain more on having the skin rather than increasing the material background.
Yeah.
Okay, thank you.
Okay, the time is over. Thank you, Sally. So LZ is a detector with data coming soon, and now we're going to the next talk is nEXO, which is a detector to be designed, constructed, and in the next few years. Brian Lenardo from Stanford will tell us about.
Yeah, thanks. Hi, everybody. So can you see my screen and hear my voice okay?
Yeah, good.
Great. So I'm going to talk about searching for neutrino double beta decay with the nEXO experiment. And my talk will very closely follow a recent sensitivity paper that we just put on the archive and submitted for publication over the summer. So first, double beta decay is a very rare form of radioactive decay where inside of a nucleus, 2 neutrons can transform into 2 protons, emitting electrons and antineutrinos in the process. But there's a hypothetical form of this decay where the 2 antineutrinos actually co-annihilate within the nucleus, and only the 2 electrons are emitted in the final state. Searching for this process in sort of second scenario is an extremely exciting experimental prospect because it would be immediate evidence of physics beyond the standard model. So first of all, it violates lepton conservation, which tells us something about the symmetry structure of beyond the standard model physics. And then it also immediately demonstrates that neutrinos are fundamentally Majorana particles in nature, both of which are sort of very exciting discoveries by themselves. It also has deep implications on some of the other unsolved problems in particle physics, the neutrino mass scale, and potentially connections to the asymmetry of matter and antimatter in the universe. So it's a very compelling and very exciting prospect to try and discover this process. The way that you look for it is you build a detector and measure the energy spectrum of those 2 electrons. Standard 2 neutrino double beta decay will give you a broad energy spectrum with an endpoint at the Q value of the reaction, which is typically a couple of MeV. The neutrinoless process, because there are no neutrinos to carry away the momentum, will give you a peak exactly at the Q value. And so the experimental challenge is to detect a very, very small peak above backgrounds and at the endpoint of this broad spectrum. Of course, this search has been going on for many years and with very stringent limits set on the process at greater than 10 to the 26 year half-lives for neutrinoless double beta decay. So the next generation of experiments really has their work cut out for them and requires a lot of the isotope of interest to have any hope of seeing this process. It requires very low backgrounds and sort of the MEV regime. If you can get it, you would like signal and background discrimination capabilities in your detector to drive your backgrounds down even further. And then finally, you want good energy resolution in order to separate this peak from the tail of this, this broad distribution, which is an otherwise irreducible background. So fortunately, as we've heard over the course of the last hour or so, noble liquid detectors are essentially address all of these challenges in a very natural way. So first and most important thing is that you can put a lot of your material into a detector and instrument it. So in our case, xenon is a very attractive technology for this because the heaviest isotope of xenon, xenon-136, is a great candidate for studying double beta decay. And of course, ton-scale TPCs, as we just saw in Sally's talk, are already being built and operated for dark matter searches. The other thing that's natural is that xenon-136 makes up about 10% of xenon naturally. And so you can easily enrich it and make a very high purity, high sensitivity search. The second thing is that the backgrounds in these detectors are very low because the intrinsic backgrounds coming from the xenon itself are very low. And then most of your backgrounds, which come from radioactivity in the detector materials, are attenuated by the high self-shielding of the liquid xenon itself. So you get a very radio quiet search region in the center of the xenon volume. You get good energy resolution with the xenon collaboration having demonstrated better than 1% energy reconstruction by combining both the charge and the light signals. And then finally, you get good signal and background discrimination, where because most of your backgrounds come from gamma rays and scatter multiple times in the detector, and your signal is more of a point-like interaction in the detector, you can use the imaging capabilities of time projection chambers to discriminate between these two things and further drive down your backgrounds. So nEXO stands for the Next Generation Enriched Xenon Observatory. And this is a proposed next generation experiment to search for neutrinoless double beta decay in xenon 136 using a single phase 5-ton liquid xenon TPC enriched to 90% in xenon 136. So here on the right-hand side, I show an illustration of what the detector will look like, where there's a copper vessel containing the TPC in the center. Directly outside of that is the cryogenics, and then encasing all of that is a huge water shield to provide shielding from radioactivity in the laboratory environment. Looking at the inside of the detector, we plan to have a monolithic xenon volume to maximize our taking advantage of the self-shielding of xenon, where the scintillation light in the xenon is detected by silicon photomultipliers, which are pasted around the barrel of the TPC. And then the charge is detected by drifting it up to the anode plane at the top, where it's measured by charge, or rather current sensitive electronics and read out directly. So what we're talking about here today is projecting the sensitivity of the nEXO experiment. And so I'll walk you through the procedure that we use to do that, starting with building a background model for nEXO. So of course, as was discussed in Sally's talk as well, for these types of experiments, the primary background concern comes from the materials that you build the detector out of. And so here, nEXO really benefits from an extensive campaign of radio purity screening and selection, which builds on the success of many other experiments, including the EXO 200 experiment, which was nEXO's direct predecessor. And so every component that will go into building the nEXO detector has been screened and selected very carefully to minimize its contributions to our background. So the plots that I'm showing here on the left is our background budget for the materials broken down by the components. So you can kind of get an idea of the level of granularity with which you've done this analysis. And then on the right-hand side is the same information, but now broken down by the material. One of the things that I want to draw your attention to is the copper. So the vessel itself in nEXO plans to be made out of copper, and in addition, the field rings will be made out of copper. So there's really a huge mass of copper in the detector, but it's not our dominant background contributor. And that's because we've decided to pursue using underground electroformed copper, which was demonstrated or pioneered by the Majorana demonstrator collaboration, and then demonstrated at large scales by the NEWS-G collaboration. And this reduces the uranium and thorium contamination in the vessel itself by over an order of magnitude compared to EXO 200, nEXO's predecessor experiment. So having really driven down the backgrounds from the detector materials as much as possible, it turns out that the actual primary contributor to nEXO's background is projected to be radon-222, which has been discussed in previous talks, emanates from anything that is wetted by the xenon in the handling system and mixes into the detector and then can mix into the TPC and decay. So the problematic isotope for nEXO is actually bismuth-214, which is a member of the radon decay chain, which gives us a gamma ray about 2% of the time, which is exactly 10 keV away from the Q value and produces a real problematic background for us. Estimating how much radon will be in nEXO comes from an extrapolation from EXO 200, and we assume a steady state population of 600 atoms in the xenon, which gives us the background budget that you see over here on the left. The next most important background is the intrinsic radioactivity of the detector materials, which we just discussed. These two things are nearly equal in contributions. And then the final component of our background model is what we call the exposure-based backgrounds, which are things that aren't affected by how you build the detector or what you build it out of. So these include things like electron scattering from solar neutrinos and the beta decay of xenon 137. This is produced by neutron capture on the xenon 136 itself, which primarily comes from neutrons produced by muons traversing the water shield near the detector. This can be largely rejected by instrumenting the water shield and using it as a muon veto. This has been studied in simulations pretty extensively, and a very conservative estimate of our rejection capabilities suggests that we can achieve 70% rejection of this background, which is reflected in our budget that you see on the left. The second piece of projecting the sensitivity of this detector is simulating the detector response. And so there's been a lot of work in the last couple of years to really improve the fidelity of our simulations. On the ionization side, we've done a lot of work really creating an end-to-end model of charge as it's produced in the xenon all the way to the collection and readout by the electronics that nEXO will actually use. Here I show an example event, and you can see that we can produce data at the waveform level that we can then analyze as if it were real data coming out of the experiment. We have a publication on this, and there will also be a talk later in this conference on R&D for the hardware for the charge readout. On the scintillation side, we've improved our modeling and estimation for light collection, first of all, by using better software. We now use the Chromo software, which is a GPU-based ray tracing software that allows us to get extremely high statistics and high granularity estimations of nEXO's light collection efficiency. And then we've also improved the optical model of the detector with extensive R&D on the silicon photomultiplier optical properties. And here's just a smattering of publications that nEXO has produced in this regard. So the last piece of both for projecting nEXO sensitivity is building a simulated data set and doing a statistical analysis. So we put the background model and the simulations together and do an analysis in 3 different dimensions. The first, of course, is the event energy, which is reconstructed as the sum of the reconstructed light and charge. This takes advantage of the fact that the charge and the light are anti-correlated in liquid xenon, effectively rotating the energy measurements and getting very good energy resolution. The second thing that we care about is a variable we call the standoff distance, which is just defined as the minimum distance between an event vertex and a detector surface. And this allows us to separate backgrounds which come primarily from the edges and which therefore show up at smaller values of this from our signal, which is uniformly distributed throughout the liquid xenon. And therefore, in the center of the detector at higher standoffs, you get an extremely radio pure and low background region with which to search for neutrinoless double beta decay. The third dimension that we use is a deep neural network discriminator that utilizes the imaging capabilities of liquid xenon TPCs to separate multi-site events, which are more characteristic of our gamma ray backgrounds, from point-like interactions, which are more characteristic of our signal. Here I illustrate how this might work with a simulated data set, which nEXO would discover a signal in with a significance of 3 sigma. So this data set was generated with a half-life of 0.74 times 10 to the 28 years. And you can see what the signal looks like. The signal here is shown in shaded blue in the energy, the DNN, and the standoff axes independently. You can see that in each one of these axes, you see a small excess above the backgrounds. And by piecing all of these 3 things together and fitting simultaneously in all 3 dimensions, we get an extremely robust discovery of a signal that would be very hard to mimic from normal background sources. So by running this same experiment with many, many toy experiments in Monte Carlo, we calculate the median sensitivity of the nEXO experiment, both the median exclusion limit with which nEXO could exclude neutrinoless double beta decay at the 90% confidence level. That's what we showed here in blue. And at 10-year lifetime, nEXO will have the capability of excluding neutrinoless double beta decay at 1.35 times 10 to the 28 years, which is about 2 orders of magnitude beyond the capabilities of existing experiments. We can also ask the question, at what half-life could we discover a signal? And that's shown by the orange line here, where again, a discovery at 3 sigma could be achieved at a half-life of 0.74 times 10 to the 28 years. So really—
We have 1 minute left.
Okay, thank you. So translating this into a new physics, you can do with this expression here, where the inverse half-life is related to the effective Majorana mass. Here I'll just show this plot very quickly, showing that nEXO pushes an order of magnitude deeper here, essentially entirely covering the inverted ordering parameter space and digging much deeper into the normal ordering parameter space. And so with that, I will conclude just to say that nEXO is an experiment that's proposed that will push deeper in our search for Majorana neutrinos and really leverages the well-established capabilities of xenon TPCs. We have a paper on this topic and then several other talks from nEXO collaborators throughout this conference. So thanks very much for your attention, and I'll take any questions if I have time.
Thank you, Brian. Let's see if there's any urgent questions. Okay, since the time is over, I will move to the next talk and can have discussion in the coffee break in get a time. Next, we have Tom Shutt, and he will talk about a GammaTPC with the liquid argon. Tom, are you there? You can share.
Hi, yes, I'm muting, and
Okay.
let's see how this goes.
Good.
Good. Let me just see if did that advance the slides? I've had some problem with that in the past. Can you see my slides advance?
Yeah, yeah.
Okay, good. Hi, so I'm Tom Shutt. Actually, my day job is working on LZ, but I'd like to talk to you today about a new idea that it's really just an idea for the future, but it seems compelling enough to spend some time thinking about. It's to put a liquid argon TPC in space to measure MEV gamma rays. Of course, at some level, this is maybe, this is sort of thing has been done before, the LC grid program at Columbia, et cetera, but we decided to take a fresh look. And there's a group of us at SLAC and Stanford who've been thinking on this. The bolded names have been working a little bit more on it than others. So why do this? This is very much change of pace from other things you guys we're hearing about at LIDINE. Key point is that MEV gamma rays, which those of us in the low background regime are very used to as a nuisance background, they scatter quite a bit, are very difficult to measure. In fact, difficult enough to measure that they essentially have not been measured. It's an unexplored region. I have a figure here. It's from one of the brightest gamma ray sources in the sky. It's an active galactic nuclei, meaning a supermassive black hole in the center of a galaxy that flares and such. And this was a measurement of a particular flare. And you see there's this big hole. This is over many orders of magnitude in energy. And there's this big hole in the MEV range. Even though this is an extremely bright object, there's nothing flying that saw it. And there's a lot of physics to do here. And this is not the right workshop or conference to try to talk about that. But roughly all sorts of things that explode or coalesce, the counterparts to the neutron star in spirals that would be seen in LIGO. Gamma ray bursts, etc. It'd be a very powerful multi-messenger probe to be able to measure in the MEV gamma rays. It's where many gamma ray sources are brightest, and so you'd have the biggest you can see a large population of events there. So this has been a long-standing issue in high energy astrophysics, is to develop an instrument that would work well in this regime. So why hasn't it been done? And the reason it hasn't been done, I mean, I mentioned it, it's because gamma rays come in and they scatter a bunch. So here is very much a cartoon of a detector. I've just put a cube of material down. This is liquid argon. And so the red dots are where energy is deposited. And that's a real Monte Carlo. That's a real event. And you can see almost like, I think there's something like 10 interactions for this event. There's a 1 MEV gamma ray. This is an imagined detector here, just sort of about a cube of a 1 meter cube of, in this case, liquid argon. So the gamma ray came in. So now let me advance, and I'm going to show you just more events. And you see indeed that, like, sometimes there's only a few scatters, but the average number of scatters is something like 5 or 6. And so what's the challenge? The challenge is you're trying to measure these various scatters, but you got to do it over a very large region, because that's just the nature of these gamma rays. They interact over a very large region. Of course, a very large doesn't mean compared to, like, say, Dune, but it does mean compared to, well, a compact detector. And in particular, and I'll show this a little more in the next slide or two, we really want to measure the location of the events very carefully, better than a millimeter. And we need it in all 3 dimensions. And okay, so let's move on. Okay, so moving on. So then what happens, I mean, this is not a pleasant way to do anything, right? Having to measure a bunch of scatters. So what do? Well, suppose you have measured all the scatters well, and I can label them 1, 2, 3, 4, 5. That's, you know, the sequence in which they came in. I have to figure that out. I have to figure out that sequence, and I'm going to do that through a set of kinematic tests of angles measured geometrically and angles measured kinematically. And to do that, I have to know the total energy of the event. I can't have inert material which ate the event or ate any of those scatters. I need the full energy, and I need all those scatters measured. And then if I do reconstruct the sequence, best case is I can say, well, if 1 and 2 were the first 2 scatters, that points back in the sky, but it points in the wrong place. The actual photon was over here in blue. It went through a scattering angle theta measured in the first scatter, number 1. I can get that theta kinematically, but I won't know phi. So I'm going to return an angle, a circle on the sky. Okay, a circle on the sky. And it's kind of ugly, but it's what you got to do in this regime. I will, if I have an ensemble of events, the circles will overlap in a spot. And, okay, fine. I've made a measurement of a bunch of gamma rays from that one direction. So that's basically going to be the game. And then realize what that means is when I have multiple events, I'm going to have multiple patterns like this. And so each legitimate gamma ray that's well measured will contribute to its peak, but will also serve as a background that sits underneath other gamma ray peaks. And so sort of everything is going to go like root n because everything is going to serve as a background for everything else. You can do a little bit better if we could actually measure the electron recoil from this first scatter. I'll never do it perfectly. If I did it perfectly, I would turn this circle into a spot. I won't turn it into a spot because, as we know, these low energy electron recoils immediately multiply scatter, and that the track isn't straight. But you will turn these circles into little bits of arc, and you will turn this rather messy picture into a significantly tidier picture. You will powerfully numerically reduce the effect of each gamma ray causing confusions with others. Moreover, this scattering, Compton scattering, is intrinsically polarized, and if you can measure the electron track, I won't talk through this detail. You will measure the polarization of the gamma ray sky, and polarization turns out is extremely important for a huge number of sources because it's a generic feature of magnetic fields, and the magnetic fields are the drivers of these jets. And so having capability to have strong polarization measurement of the gamma rays adds a lot to the astrophysics that you would measure. So measuring this electron track is really a big deal if you can do it. All right, so what have people tried to do before? On the right is the one instrument that has flown. It was called COMTEL. It's sort of 1980s technology, maybe even late 70s technology, finally flew on what was called the GRO. And it kind of had a front detector and a back detector, and they're, by modern standards, very crude. But more recently is something are attempts to do it with silicon strips. So again, I've mentioned before, the events are at least around 30 centimeters on the side. So you want a detector that's much bigger than that. You want to do full measurements in 3D of all the events. You'd really like to measure, if you want to measure the event location, you need to measure the head of the electron track. And it turns out, if you go through numbers, you want to measure it to better than a millimeter. You need good energy resolution. You want very low passive mass, because if you have 5 scatters and you have maybe 10% inert mass, you have 5 chances for something to get lost. You want high uniformity. Okay, so lower left is what is sort of the best technology now, and it's a set of silicon strips, and it's just expensive to do it that way. What's being proposed on a probe class mission, this is sort of let's call it $1 billion scale mission. Although there's also people are talking about sort of a third that cost missions that are not quite as powerful as what I'm showing you here. This is called Amigo. It has 60 layers of silicon, and that gets you about the equivalent of 5 centimeters of liquid argon. And then you have to have cruder detectors behind that, and there's kind of a cost optimization here. That's current technology. And here's kind of what we're pitching. This is a cross section. This is just a 2D CAD, right? If you're looking from above, you'd be seeing, it looks like it's a section of a sphere or hemisphere with, hexagonal segmentation. So segmented, it's a set of segmented TPCs. It might be something like 20 to 30 to 40 centimeters. I think 40 centimeters thick would be good. Liquid argon for a variety of reasons that I could maybe answer in questions. What I'm showing is kind of like if this thing really, really, really works, and this would be a dream instrument, you could get to a few meters on a side, so maybe a 10 meter squared instrument, which is vastly larger than anything people can contemplate in silicon for reasonable cost. And it would be a heavy instrument, but on the other hand, and this is real, SpaceX has dropped the cost of launching mass into space. So that makes this really compelling. There's really two constraints going into space, mass and power. Power means kind of channel count in electronics. A TPC famously only has two-dimensional readout for 3 dimensions of imaging. So instead of layers of silicon, we just have a TPC. And that meets the power consumption in space. And then the mass in space, well, mass is dropping. The cost of launching mass is dropping quite a bit. Other than that, in some ways conventional, we'd have a cathode in the middle and light and charge readout on the edges, and we'd probably put SIPMs on that central layer. We talk a little bit more about the charge readout. There's kind of an interesting thing. If you try to read fine scale, diffusion is your enemy in a number of ways. I mean, in a simple way, it washes out the signal. But in another way that's key, and again, let's not look at these figures yet, but just upper right here, this one plot. If you have fine scale pixels, I could pick pixels, or if you did strips, you get the same story, like grids, fine scale grids, if you could do it. If you make them very fine, the problem is events diffuse, and some of your charge diffuses out and becomes sub-threshold. And this is just a calculation of how that might transpire, and the horizontal axis is drift depth. And you see, if I try to go to fine scale pitch, and we do want to be sub-millimeter, I'm going to lose much of the charge from deep events. So we've come up with a way around that. Whether it will work or not, good question, but we think it's interesting anyway. Let me start in upper left. Here's the TPC. Here's the overall instrument. Any one segment looks like EXO, central cathode, anode. Zoom in on what the anode region looks like. What we're proposing is that you'd have grids that are sort of centimeter pitch. The charge cloud would drift past. Centimeter pitch is big compared to diffusion. It will still be essentially point-like charge cloud up to several MeV. And you measure the integral signal without much loss due to diffusion. And then you drift the charges further, and there's pixels. And then you'd measure the pixels in detail, and you'd image the track. There's also a second thing, that having pixels, a huge amount of pixels, especially say 0.5 millimeter size pixels, is a huge channel count, and you might have an enormous power. We're going to trigger on the coarse grids to turn on the pixels, and that can give you a very large reduction in the power. At least around 10 to the 4. And then that makes the thing on paper all work. I have a quick slide on the pixel readout. This is really just to advertise that there's a group of us, several of the electrical engineers who've worked on these sorts of things in the past, the cryo-ASIC chip that's going to be used for nEXO and was being looked at for Dune. A variation on that, on this architecture, and I won't talk this through, looks like it could actually work, although we've got to develop power switching in a way that's been done before, but there's some novel aspects of how it has to be done that are a little bit of a challenge, but may well be quite doable. We're going to have to see. Oops. What would you actually do? This is a movie, I hope it starts. Yeah, this is an electron track. It's a high fidelity simulation of an electron track using a Penelope program. You see it's an MEV, and it's a few millimeters, about 2 millimeters long. This is read out with an imagined 300 micron pixel. We can talk about the assumptions that went into it. I think they're sort of semi-credible. And your goal is to measure the head, which is the red dot, and even this little faint red arrow, which is the initial direction from the, and to determine where the head is. The tail's over here and it's heavier. You can see that. And the cartoon, of course, is the effective diffusion. And you see the track doesn't get fully washed out, but certainly it's better the closer it is to the anode. And we took a quick look. We used machine learning, and it doesn't look bad. It looks like you can measure sub-millimeter. The head of the track. Moreover, this is the cosine. Over on the far right, this curve going up, that's good. Okay, I'm not going to talk through all the details, but essentially, this lower curve here on the right is showing that we are measuring this initial direction on average for most events. And in fact, we're doing it down to around 500 keV. That's kind of remarkable. This, for instance, might be of interest to double beta decay, although eventually the diffusion would wipe you out on an instrument the scale of nEXO. Okay, can we stick a tiny version of Dune in space? Well, that's not going to be for the faint of heart. There's a bunch of issues. Biggest issue probably is space charge. There's a high event rate in space. We don't have the atmosphere, and big rate of cosmic, all cosmic rays. And so you'll, for sure, there's going to be space charge. We'll basically need to neutralize it in an ongoing fashion. And numerically, if you kind of work through numbers, and I'm sorry, we could do this with a scheme that had a photocathode and an LED or a laser, and it's sort of like in terms of power use, et cetera. If you had a quantum efficiency of around 10 to the -4, this looks like it could work. That'll have to be developed. Cryogenics will be challenging. I mentioned that there's a big reduction in the power for these pixels using this triggering and a charge on-off scheme. And if that all works, then yeah, it looks like you could do this with conventional coolers. You'd probably run this hot. You'd run it on about 120 Kelvin with high pressure in order to make the cryogenics easier. But that looks doable. Maybe even passively cool, although that looks probably maybe not going to work, but maybe. Finally, you're going to have to separate the liquid and gas phases. You don't have gravity up there. So presumably there's going to be some sort of expandable bellows to put the liquid under pressure. Another approach is you just simply spin the spacecraft and create artificial gravity. And in fact, there's some literature and understanding of how to do that because people that work in space are thinking about how to put liquid oxygen and liquid hydrogen in storage modules up in space. And there's some understanding of what this will be like. So there's a lot of work. There's a lot of work here to do, but okay, maybe it's all doable. Quick look at performance. I'm showing you curves in an unfamiliar, I guess, for most of you, field. Really, the point would be we compared ourselves to this probe class, this billion-dollar scale mission. That's the black line. The purple line. This is sort of preliminary. We put in a range of assumptions for how this detector might perform. This is angular resolution. You want lower. This is the effective area. This you want larger. Energy resolution you want lower. And you see we're kind of comparable in some measures better than this proposed mission with silicon strips. And I think we're far from having optimized our understanding of the performance, especially actually just using the standard code that's used in this field. It's not really designed to study to handle this detector. And perhaps we're going to do a good little bit better than these curves show, but I can't promise that. Key point, though, is that we promised to get a much larger instrument. If we could get like an order of magnitude larger instrument for even a smaller cost, that would be the goal. In fact, I think this program, the idea would be to work to do what's called an Explorer class mission. That's more like a few $100 million, of which the detector would be, say, a $50 million instrument. That's a whole model that sort of could work. And would really, if you could do that, if you could do a 10 meter squared instrument for an Explorer class mission, which does not require, rising to the top of a NASA decadal plan, that might be doable. Okay, so conclusion. I think, the science case for doing an MEV mission, I believe is compelling. NASA is trying to figure out something to do in this area. There's a group of people that really want something to fly. Maybe a nice outcome would be that the small-scale silicon version flies soon, and then this would be a successor mission, say a decade in the future. Clearly, there's a big development here. Liquid argon TPC is promising. If this all worked, obviously it's a huge leverage of the work that all of us in this conference have done, and the advances in the last 20 or 30 years, and more specifically the huge investment in Dune. It hits a sweet spot. TPCs, and I've said this, but let me say it again, TPCs allow you to get a large detector with small channel count. That now, 10 years ago, pre-SpaceX, it wouldn't have helped, because launching it several tons into space put you into a very expensive billion-dollar class mission. Now, many-ton detector looks like it could probably be in an economical mission, and the TPC gives you the commensurate low channel count. Many challenges left to solve, but if you did solve it, I think this would be a transformational instrument. Thank you for your time.
Thank you, Tom. This would bring us a new field using noble liquid, noble element for space astrophysics, which was not possible a long time ago. Some blue flight was done, but not space flight. And a question. Elena.
Hi, really nice talk, thank you. Maybe I missed it, but what is the expected event rate that you have in the geometry that you're thinking about?
Oh, it's pretty brutal. If I remember right, it's on a scale of about 10 kilohertz per meter squared. And so, for instance, the segmentation is needed for a number of reasons, but first off, just for event rate. And so that kind of picks the size of these voxels, and then the space charge is brutal. But if you solve it, it all looks doable with charge drift lengths of this would segment us to, like, say a 20 centimeter, 15 centimeter drift this way, and 20 centimeter drift below, 30 centimeter drift below, and it all just kind of works. I don't know if that answers your question. It's about, I believe it's around 10 kilohertz per meter squared. It's very dependent on the energy and how much material is outside the detector, et cetera. But.
Okay.
Okay, thank you.
Miss Sen, is that the correctly pronounced your name?
Yeah, good enough. Thanks. So why liquid argon at 120 Kelvin? Maybe you mentioned that, but I missed it, because depending on the conditions, you might be in. It might be too warm or too cold to keep the argon actually liquid.
Yeah, no, good point. I picked a high temperature because if you look at either passive cooling via block body radiation, which is one possibility, or cooling with cryocoolers, essentially, the modern type of cryocoolers. There's a whole development of those for space. You need to keep everything as simple and kind of commodity-like as possible. And it turns out the cooling power is a very strong function of the temperature of the detector. And so you make it hotter and hotter, the cryocoolers get cheaper and more reliable, and there's more of them. So I picked a high temperature with the trade-off being that then you need a pressure vessel. The pressure vessel, in addition to, like, you have to fab it, but maybe that's fine. More material serves as inert scattering that you don't want. It screws up your events. So 120 Kelvin gives me about a 20 or 30 bar pressure vessel, and sort of that's a guess as to what might be the right thing. You're kind of asking partly a different question. How do I keep it at 120 Kelvin? Well, that's going to be the work of the cryogenic system. And realize the cryogenic system by itself is only going to put it at a temperature. And as we all well know, at a temperature, it wants to have both phases. So we're going to separately have to solve the problem of keep it a liquid while the cryo plant keeps it at 120 Kelvin. I sort of mentioned this in another slide. I think the answer there is some sort of expandable bellows arrangement, or another way is you actually just spin the whole instrument and create a spot in the center where it's gas, and all the rest will have artificial gravity, and that will separate the phases. But that's a real challenge.
Tom, I have a question. This is similar to the dark matter field. Why you choose argon instead of other elements, and why not using high pressure? Sometimes will give you maybe better energy resolution and the position resolution.
Yeah, it's a really good question. I mean, I think the basic issue, you saw how big the events are. The events are you need, for a low Z material like argon, you need at least 30 centimeters cubed just to be in the game. And that will have many events spilling out the outside. So we need a very large detector. That's how thick it has to be. So gas, it'd be a massive detector to have enough mass. So I think you have to have liquid, or density near 1. Of the nobles, because I think a TPC is a real, is a good way to go. Really, krypton's radioactive. Neon, of course, has bubbles. Helium has bubbles. So it's argon or xenon. You actually want the light material, not the heavy material, because the heavy material doesn't afford you many scatters. The photon is quickly absorbed. And it turns out your first instinct is, oh, that's no good. I don't want 5 scatters. Well, if you're going to do this kinematic reconstruction, you do want 5 scatters. You don't want several scatters. You want a bunch, because then you're much more powerfully reconstructing. There's other arguments as well. If you have a low Z material, then you have a wider energy range over which you Compton scatter. At high energy, you pair produce. And in fact, it turns out until you get very high energy, it's really hard to use pair producing events. So you'd rather optimize the range over which Compton scatter dominates, and especially on the low end. You don't want photons coming in and just being photo-absorbed. You can't do any pointing with that. So argon wins in that matter. And finally, I'm giving a big answer to a short question. If the key real question is comparing the distance between scatters to the electron track length, and even more so, the diffusion. And it turns out if you compare xenon and argon, the ratio of the electron track to the mean distance between scatters at an MEV, say, is favorable by about a factor of 2 in argon compared to xenon. And then the diffusion is about a factor of 2 better in argon than xenon. So there's kind of a factor of 4 intrinsic capability to measure this electron track and find its head, i.e. get the event location compared to the distance between. And that's giving you your scatter arm, your lever arm to do angular resolution. So intrinsically, I think the angular resolution is about 4 times better by some vague measure in argon than xenon on basic principles, independent of other readout aspects.
Okay, thank you very much for the answer. Let's hope, in the next 20 years, we'll send a noble liquid detector to the space.